Okay, so welcome to the second day of MSFP. In this session, we will have two talks, and the first one is by Annie Baanen and Wouter Swierstra. Will be presented by Annie, and it is about combining predicate transformer semantics for effects, in particular for parsing regular languages. The floor is yours.
Thank you. Yeah, and thank you all for attending. So, let's just get right into it. So what we're interested in this case is to look at how we can verify algebraic effects. And well, the really nice thing about algebraic effects is that we have this strict separation of the syntax, how the primitive operations, the primitive effects are sequenced, and the semantics of effects. So like how to assign meaning to those operations. And what we did is we took out a verification project in ACTA using the free monad to model effectful programs. So you can see here we have a type C of commands and a type R of the responses of the commands. And then a program in the free monad is either pure computation, so there are no commands, or we do an operation and then we get a continuation in which we can optionally do some more effectful operations. And the first example that is quite important to us is non-determinism. And we have this non-det monad that we model as an algebraic effect with two primitive operators. We have the choice operator, which non-deterministically chooses between two values, and the failure operators, which goes to a failure state and stops execution. But of course, these two bullet points, they are really the semantics. So you could as well choose that choice is a probabilistic choice. But in any case, the syntax consists of two parts. We again have the commands with a choice operator and a fail operator, and then we assign return types to these commands. So the choice is a non-deterministic choice of a Boolean, and failure returns nothing because we fail. And then the way to assign semantics to an algebraic effect, system with algebraic effects, is typically you give a handler. So, and these, for the free monads, they arise very naturally as just a fault over the free monad. So in the pure case, if we want to collect a non-deterministic program, we want to collect all the results of this program into a list. Then we write it as a fault. With the pure case, just put the return value in the list. And then if we have a choice, we combine the return values of the two alternatives. And if we fail, then there is no return value. And basically, what we did was we said, well, what happens if we don't want semantics that return a value, but what if we want semantics that return a predicate? So let us look at, let us take this fault, but now return a predicate of type set or a proposition of type set. So we're in ACTA with constructive type theory. So our propositions look like sets. And then what we do is we have two arguments, one for the op case and one for the pure case. In the pure case, we apply this P, and in the op case, we apply this algebra, which says for each operation C, how to interpret the semantics of the continuation. And if we stare at this for a bit longer, we might come to the conclusion that it has something to do with predicate transformers. So really the thing that DEXA was already doing back in the 70s is that we have like a function from postconditions to preconditions. So yeah, suppose we have some type of command C and some type of responses, return values for each command R, but now the responses don't depend on the type of command that we choose. So our postconditions will have type R to set, our preconditions will have type C to set, and the predicate transformer is just a function from R to set to C to set. But now we're in ACTA with dependent type theory, so let's make R depend on C, and then we need to reshuffle the type a bit, and we get the following type of predicate transformers. So we take the command, then the postcondition, and then we return a proposition, which is basically the precondition. And this is exactly what we get that we when we take this generic fault. So the algebra that we pass to the semantics function is exactly this type of predicate transformers. So that is the reason that we say we have predicate transformer semantics for algebraic effects. And what we can do is look at some different semantics. So here we have this separation between syntax and semantics. We have this the non-determinism syntax, and now we can choose different semantics for them. For example, there are the two canonical choices. If we have either we want all the non-deterministically possible results to satisfy our postcondition, or we want any of them. And we can express this with this pt all or pt any predicate transformer. And what will look is, how it will look is in the failure case, then we have no response. So all the potential results are trivially true. And if we have a choice, then both of the alternatives should satisfy this, this postcondition. And for pt any, it's exactly the opposite. If we don't have any response case, then the postcondition will never be satisfied. And if we have two responses, then we can choose which one of them we want to satisfy. So until now, this was, we already kind of knew this. We already published this in ICFP. But we were kind of looking for, how can we prove that these semantics are also useful in practice? And for that, we used a nice example, which consists of a parser for regular expressions. So here is a data type of regular expressions in ACTA. We have the empty regex that doesn't match anything. We have the epsilon regex that matches only the empty string, and so on. And then we want to parse these regexes into a parse tree. So for each regex, we have like a type of the parse trees, which is just matches exactly what you want for the regex. Okay, so let's implement this match function as this non-deterministic program. Given a regex and a string, we return a parse tree. So for the empty regex, then there are no strings that match it, so we just fail. For the epsilon case, the regex that matches only the empty string, then we do a case distinction on the string. In the nil case, in the empty string, we succeed and we return true, and otherwise we fail. And so we can go through all these cases. So here, for if you have an alternative regex, either left or right, then we use this non-deterministic choice. And so we go down all the options until we reach this Kleene star. So, and if we try to define it as follows, like the Kleene star is either the empty string or concatenation of R with the Kleene star, then what we get is an error. ACTA doesn't like this definition because it, in fact, it does not terminate. We cannot give this definition like this. So there are ways to fix it, but for now, let's just kind of give up and say we'll just fail in case we encounter a star. So suppose that we have this definition with where we fail with the star. We can still give a useful specification for this. So namely, doing this again in like this predicate transformer style, our specification should be a precondition and a postcondition. The precondition will be there is no star in the regex, and the postcondition will be defined as this inductive data type, which says when does a regex match a string with the correct with a given parse tree. And then what we use is an idea of the refinement calculus to check that this specification is also implemented by our matcher. And in the refinement calculus, you use a refinement relation to kind of compare two predicate transformers. And the idea is if we have two predicate transformers, then the first one is refined by the second one if the second one is better in the sense that it satisfies more postconditions. So we have this definition of a refinement relation. which says for all post conditions such that PT1 satisfies it, so should PT2. And more specifically, if we assign predicate transformer semantics to programs, then this refinement relation kind of means that if we have a program that calls S, and S is refined by T, then anywhere we can, in this program, we can replace S with T, and we get a program that satisfies at least the same amount of post conditions. And in the refinement calculus, this is used for incremental deriving of a program from a specification, because the nice thing about the predicate transformers is that they can also be mapped. We can also map specifications to a predicate transformer. So we can relate programs and specifications in the language of predicate transformers. And the predicate transformer semantics for a specification is that post condition, predicate P holds whenever we have the precondition and the post condition implies P. Okay, so now we have our specification, we have our refinement relation, and we have our program, so we can start proving the correctness statement. And this will look as follows. The precondition and the postcondition are refined by the match program under the PT all semantics for non-determinism. So all the output of match will satisfy the postcondition if the precondition holds. And there is not really too much to the proof. You just do the same case distinction as in the definition of match, except that you need to be a bit clever to deal with this bind operator. And what we then need is a rule of consequence. So this was already something that Dijkstra was thinking about. So if we have a composition of programs S bind F, then the semantics of that you can express as in terms of the semantics of S, whenever you, if you can compute the semantics of f of x for all x. And then if you just substitute along this equivalence, then you can understand what the bind operator does, and therefore prove what, prove this refinement relation. Okay, so that concludes the first part. We have a match function, but it has a bug, namely it doesn't support the cleany star. And for that, we to fix that, we kind of need to add an extra effect to what we already have. And we want to add more effects to our system. And the nice thing about algebraic effects and the free monad is that we can easily add new effects to our system without really having to change the previous definitions. And in our case, what we do is we had this free monad before with one command type C, one response type R, and now we replace that with a list of signatures, so a list of C's and R's to get, and the pure case is exactly the same, and in the op case, we kind of take this index into this list of signatures. And the two effects that we'll use in this paper are general recursion and parsing. So general recursion is uses this idea by Conor McBride and Turing completeness totally free. We can model the general recursion like a recursive function of type I to O by adding the signature with command type I, so call the function, and response type O, the return value of this function call. And well, this is kind of the most general signature that we can imagine. So to specify semantics for such recursive calls, we need some more information. And again, we get some concepts already around for 50 years. We need an invariant to talk about loops. In our case, we say an invariant is a relation between the input type and the output type. So we say which output values are valid for a given call, for each given call with a given argument. And the semantics, we call that PT-rec, the predicate transformer semantics of recursion. And the second effect that we'll add is parsing. So parsing really is a stateful kind of program. because we have an input string, and as the parser runs, it advances the input string character by character or token by token until we run out. So let's model this state with an effect. And to be more precise, we model it as an effect with one command, which returns maybe a character. And then if the string is totally consumed, then we return nothing. And if there is still some more characters in the string, then we return just the first character. That would be the intended semantics. And to model these semantics, we incorporate state into our predicates. So where before we had just, we would have R to set, so maybe character to set. Now we have to augment our predicates and put the current state, which is the part of the input string that we haven't consumed, into this predicate. And if we do that, then we can just thread the input string through the predicates, and we get the semantics of parsing. Okay, well, for finishing match, we only need this general recursion. So we can finish our definition by saying to match R star, we just we recur on either matching epsilon or R composed R star. So now we can prove our correctness again without this previous precondition. Now we just say in all the cases that we run match, it will satisfy the post condition, i.e. it will give a valid matching. And this result that we have here is only the weakest liberal precondition, really. It's only partial correctness of match because we do not check for termination. And moreover, if R if it matches the empty string, then match will not terminate. So, and that is because in the semantics of recursion that we took, we assumed that all the recursive calls immediately return because we don't do any checking of the bound on how many recursive calls we make. But that's no problem. We can add that later because we have this separation of syntax and semantics. We can just add a more detailed semantics later. So for now, to check termination, we should make a new version of a matcher that really does terminate. And the trick here is not to do recursion on the regex. We should do recursion on the string. So we should consume the input string one character by one character, and then we use something called the Brzezowski derivative, essentially constructing the finite automaton for a regex as we parse the string. So we have this derivative-based matcher, which again takes this regex, but now we incorporate the effect of parsing, advancing the input string by one character, into the list of effects. And so you don't see this string appearing here in the type. And the derivative-based matcher calls the parser effect. And in the case that we can still advance the input string, that there is still a character x, then we go in recursion on the derivative of the regex, and we reconstruct the output using this integral tree function, which kind of is the antiderivative for the tree function, for the tree type. And in the case that the parser effect returns nothing, so we have run out of the end of the string, then we just check, does the regex match the empty string? If so, we return the appropriate parse tree, and otherwise we fail. And it should be clear that this terminates if we use the correct semantics for effects, because we can, each recursive call, we advance the string by one character. So again, it's now we can prove the soundness and of the dmatch function. And the way we do it is we show that match, this function that we defined before, is refined by dmatch. And that means that like using the concepts of the refinement calculus, we can replace match everywhere with dmatch and we'll get the same results. And now the other half is that we have this termination checking that we need to do. So as I said before, we have only the weakest liberal preconditions to semantics for PT-rec. And so we need to add some sort of termination check. In this case, what we'll do is just define this termination check directly. So we have, suppose we have a recursive function f, a general recursive function, and then we have a program S that can call f as part of an effect. And then we say this system terminates in n steps, if and only if, well, we can substitute f at most n times, and then we have termination. So, well, if the program is just a pure computation, then obviously it terminates. If we call if we do a recursive call and there is no more fuel left, we cannot. It does not terminate in n steps. And then otherwise we have like the successor case. So we do a bind in the program, and we check. So we do this recursive call on C, and then we do the rest of the program. And this should terminate in n steps. And then finally, we use the predicate transformers for the other operations to check the termination for any other operations. Yeah. So now we can conclude the total correctness of this dmatch function, because on the one hand, we have this chain of refinements. So we have our specification, which is refined by the match function, which is refined by the dmatch function. And we can also prove that the dmatch function itself refines the postcondition. So that means that not only does all the output of dmatch satisfy the postcondition, but also all the correct output is returned by dmatch. And then to add to this partial correctness, we add total correctness, which is just a proof that this terminates in predicate holds for dmatch. And yeah, as I said, it's not too difficult. Each recursive call consumes one character of the string. So indeed, it will terminate in the length of x steps. So that's a quick overview of our development. Our goal was to kind of investigate the practicality of these predicate transformer semantics for effects and try to use these concepts from the refinement calculus to do functional programming instead of imperative programming. And what we saw is they really do provide a natural and uniform way to reason about effects in the setting of the free monad. And yeah, the reason that we like them is that they are very modular, these semantics. So we can add new effects and new semantics to the system as we need them, and we don't need to change our programs that we already have. We can just keep the old syntax and start with the new semantics. So a formally verified parser is really nothing new. They have been developed before. But what usually happens is there is this specialized semantics, usually also part of the syntax of the program. And these semantics have been really specialized to the domain of parsing. And so they don't really allow you to reason uniformly about all effects in the way that the algebraic effects should allow you to do so. And especially one distinguishing characteristic is how we deal with termination. So with these algebraic effects, we can talk about the partial correctness and the total correctness independently of each other, and makes it quite easy to deal with both without having to worry about one when you're proving the other. Okay. So I hope that people start to use predicate transformer semantics also in functional programming, because I think they are a really nice solution for verification. Well, thank you for your attention, and feel free to ask any questions.
Thank you. Questions? I can maybe start from some silent questions and then give the floor to some of you that want to ask questions yourself. So Jeremy Gibbons asks, Bob Harper's JFP Perl seems to have been a seminal paper in the sense that it has seeded many follow-ups. There was another last week at ICFP, strong functional Perl, Harper's regular expression matcher in Cedil, by Aaron Stump et al., which avoided the need of dependent types by using, quote, quote, a certain polymorphically typed interface we call a recursion universe instead. Can you compare your paper with theirs?
So I haven't read that paper, so I cannot give an argument. Cannot give a reply right now. Yeah.
Good.
It's I'm sorry. I will have to
something
read
to
that.
check. No, sure. Andrew Hirsch asks.
Maybe Wouter knows the.
I could maybe say something. So the Stump paper, there's a few versions of which have verified this functional curl. There's also one by Dan Licata and his students who do a intrinsic verification. The paper by Aaron and his students is more kind of Sedil specific, and it uses like a variant of a Mendler style recursor, and with a kind of combined with the paramorphism in order to show termination. And then the Licata version is actually quite nice in that it uses a trick. It defunctionalizes the matcher, and then this is kind of interesting because defunctionalization it tends to be this whole program transformation, which often kind of screws up your termination behavior. But in this way, it messes it up in just the right ways to make your program structurally recursive, which is slightly interesting. I think what's different here is that we managed to tease apart the entire verification problem into several different steps. So you can start by writing the easy cases, and then you add effects to support general recursion, and then later on you show that it is indeed terminating, and each of these problems can be split off as a separate verification challenge, which arguably requires a level of indirection which takes some getting used to, but is arguably more modular, I guess, in the verification, that you can separate the termination proof from the actual correctness. Is that an answer, Jeremy?
Yeah, not sure. Jeremy's
yeah, sorry, still trying to read as well.
Okay.
Yes, thank you. That's very helpful. I was just about to reply in Zulip. Chris Jenkins is also watching this, so maybe Anna and Chris might like to have a chat.
Indeed. Okay, let me read out another question by Andrew Hirsch. What is the relationship between your semantics and Dijkstra monads? Is it the case that your algebraic effects give rise to Dijkstra monads?
So there is quite a deep relationship to our work and the Dijkstra monad. So you could see the Dijkstra monad as a bundled version of where you take the free monad together with its specification. You kind of bundle this together into one object, and it has its advantages and disadvantages. So what we like is about our semantics is that they are really separate, and so we get this modularity that is quite nice. But on the other hand, with the Dijkstra monads, you put your proofs together with the item that you are talking about. So it's the way combinations of programs work is I do feel a bit nicer, for example. But I think there are many ways to arrive at these predicate transformer semantics, and I think we're all kind of groping towards the same conclusion in the end.
I think so too. So I think yours is also very much related to what Niels was discussing yesterday.
Indeed,
so,
yeah.
Yeah. So, Kimi, you wanted to ask a question. Do you want to ask it yourself?
Sure, why not? So I have been looking at McBride's Turing completeness totally free for some time, and I've always been stumped by this part where I really don't see how it actually works when it comes to composing recursive functions. I mean, the essence of the paper, as I understand it, is that given a recursive function, you stub out the self-reference. In other words, you reify it, and you put a piece of data there. It's a bit like in free monads. You stub out your effectful functions and your effectful values, and you interpret it using what we now, I think, call handlers. It used to be called interpreters. So what happens with two independent recursive functions is that you've each got this self-reference, and when you compose them, it's not obvious. It's like well, you can only have one self-reference now. It's like so where
Right.
do you, what does that mean? And so I can't see how you could compose it. So, but you say you use this technique in your work. So what happens?
Right. So suppose you have like a recursive function f that can call itself and a recursive function g that can call itself.
Yes.
And then
that
your
calls
question
itself,
is,
yes.
like how can we talk about the composition of f and g in the
Yes.
free monad or in the
in the TCTF monad, yes.
So there you would use combinations of effects. So you would include them both into a free monad with two effects, where one is call f and one is call g. And then in that monad, you can take the composition of the two. And I presume that then, you would handle the calling f with one handler and calling g with with another handler, and then in that way.
So there will be two self-references, I suppose.
Yeah, so you would basically have
Yes.
call f as an effect and call g. And then,
And this can be done in ACTA.
Yeah. I'm
okay.
pretty sure that's no problem.
Okay, well, I wrote a simplified Haskell version of it, and I couldn't get it done. But thank you for the answer.
Of course, you're welcome. Thank you for the questions.